My name is Kamal Gupta, and I'm the engineering manager of Aurora MySQL. Today, I'm going to talk about not only the new innovations in Aurora, but also how we did it, and how we are adding new capabilities like multi-master, global database, machine learning, managed proxy into our Aurora offering. With me, I have Kotaro Fukawa and Shunichi Kaneko from Nintendo and DNA to share their success with Aurora in their production cluster. You know, Amazon.com runs on Aurora, and now Mario Kart 2 runs on Aurora. Previously, my wife can tell me if Aurora is not working. Now my kids can also tell me Aurora is not working. All right, so let's jump in. Amazon Relational Database Service was built with a simple mission: to free you guys from running and managing databases. So you don't have to worry about time-consuming administrative tasks such as database setup, provisioning, monitoring, scaling, patching, backups, and instead allow you to focus on your applications. RDS is available in multiple instance types options, optimized for memory, I/O, and CPU, and comes with different database engine flavors, including open source like MariaDB, MySQL, Postgres, commercial grade like Oracle, SQL Server, and our own Aurora, a cloud-native database. Now, the question is, why did we build Aurora? On the one hand, we offer commercial-grade database engines that provide enterprise-grade performance and reliability, but they are expensive with complex license management. On the other hand, we have open source solutions that provides the simplicity and cost effectiveness, but they lack enterprise-grade performance and reliability. Our customers wanted the best of both worlds. That is, speed and availability of high-end commercial databases at the cost and simplicity of open source solution. And that is our value proposition, and that is what we are going to talk about today. By the way, Aurora comes in two flavors, MySQL and Postgres, and so you guys can choose, depending upon your application needs, which one will fit better. So I'm going to first talk about performance and scaling, and then jump into availability, durability, and manageability aspects. Sounds good? All right. Aurora is a scale-out, distributed log structure database. And what I mean by that, if you look at Aurora under the hood, Aurora is striped across thousands of storage nodes, with each data 6 ways replicated across 3 availability zones. So there are 2 copies in each availability zones. With Aurora, we made 2 key innovations. First, we pushed the log applicator down to the storage. And this matters because unlike traditional database engines where they have to write both logs and pages, database pages, we just have to write the logs because we can construct the pages dynamically in the storage itself. And that means we have to do significantly less I/O and much less work on the database engine. And that allows Aurora to scale much better in terms of throughput. Second, instead of using heavyweight consensus protocol like Paxos or Raft, we use lightweight consensus with 4 out of 6 quorum and local tracking. The reason we can avoid heavyweight consensus is because we exploit the monotonically increasing log sequence number in the head node to order the writes. And that helps in Aurora to perform in terms of latencies and minimize the jitter. Now, we're going to go in both of them in detail and talk about in a little bit more detail how it works and see with more graphics why it makes sense. So here I have the first log applicator in action. As you can see, I have master and replica on the top and storage at the bottom 6 ways replicated. Let's say T1 started. As you can see, all the storage node and replica receive the changes. And so if master and replica have to read, they will get the latest version of the page. That makes sense, okay? Now, let's consider a more interesting example. Let's say T2, T3, and T4, they all started. And as you can see, the storage node only coalesced the blue changes, but kept the red and green changes on the side. And this is because, if you notice, the replica clock is still at blue, because the replica has not yet received the green changes. And so if master and replica have to read now, they will get the right version of the respective pages. And for master, the storage node will apply the delta log records, that the log records in green and red, on the fly, on demand, to construct the right version of the page. And let's say at some point, the replica catches up, and now replica clock is also green, I mean, you got everything. At that point, the storage node can garbage collect and coalesce those log records. So hopefully you can see how we can construct the pages from the logs themselves. And so we don't need to send a separate log stream. And that allows us to perform much better in terms of throughput. Here, we ran Sysbench on 16XL, comparing Aurora with stock MySQL running on EBS in a cloud environment. And as you can see, Aurora performed over 10 times better in terms of write performance, and 2.5 times better in terms of read performance. Now we support R5 instance class all the way up to 24XL. So 24XL comes with 768 GB of RAM and 96 cores. So we can vertically scale all the way to 24XL. Let's look at the second innovation in action. Again, I have storage 6 ways replicated on the left, and I have durability and commit tracker on the right. Let's say at some point, T1 persisted the changes to 4 of the storage nodes. So as you can see, the durability tracker for T1 bumped to 4. And because we only need 4 out of 6 quorum, we can now acknowledge T1 back to the client. Now let's see, at some point, the picture may look like this. Now, notice that T3 achieved the quorum. So it has 5 out of 6 quorum, but T2 did not achieve the quorum. It has only achieved 3 out of 6. That's not enough. Now, this is possible in Aurora because we immediately send the writes down to the storage in parallel to minimize the latencies. But of course, in databases, we cannot have holes in the database logs. Right? That doesn't make any sense. And so what we do instead is we have this durability and commit tracker on the database node that we use to make sure everything until that point has to achieve quorum before we acknowledge the commit. So in this case, we cannot acknowledge T3 yet because T2 has not achieved the quorum yet. Now, let's say at some point later, T2 and T4, both of them achieved the quorum, and now we can acknowledge all T2, T3, and T4 back to the client. And so hopefully you can see how we are using the lightweight consensus, 4 out of 6 quorum with some tracking on the database node, rather than using some heavyweight consensus protocol with multiple round trips and synchronization points to slow down the system. And as a result, Aurora performs much better in terms of latencies and have much less jitter. And the reason we have much less jitter is because we use 4 out of 6 quorum, right? If 1 or 2 storage nodes are slow, that's totally fine, because we just need 4 votes. Here, again, we ran sysbench on R4 16XL, comparing Aurora with MySQL running on EBS in the cloud environment. And we observed 25 times better latencies and over 100 times less jitter as compared to stock MySQL. Again, this is because ability to do out-of-order writes and lightweight consensus. By the way, the 5 big spikes that you see in the graph, they correspond to MySQL checkpointing. And the checkpointing process, just for the background, is a periodic process of flushing the pages onto the storage. But with Aurora, because we don't have to flush the pages, we don't have any checkpointing. And so we don't have this background process that is interfering with the foreground activity of the database process. Okay, we talked about DML throughput. We talked about DML latencies. We talked about jitter. What about scale? Let's talk about read scaling. On the left, I have MySQL native bill log replication. And the way it works is it creates a separate logical stream. And so at the time of the commit, now the database stream and this logical stream have to be synchronized, which means I have to do 2-phase commit. And that slows down the master. Second, because it's logical, I have to replay the exact same SQL statement on the replica. Right? And because I have to do that under heavy load, that causes lag. Moreover, I have to do all the write I/O and I need a separate storage, and it's so costly. When we thought about this in Aurora, we completely re-architected it. We said, why don't we use the same stream that we are sending to the storage? So we don't have any logical stream for Aurora replicas. So you leverage the same stream, so you can add more replicas, have no impact on the master performance. And because they are physical logs as opposed to the logical logs, I don't have to execute them like SQL. I just have to update the pages in the cache on the replica. That's a multiple order of magnitude lighter process or lighter job to do. And moreover, because the shared storage, I don't have to, there is no extra storage and there is no extra I/O. Just to clarify a little bit here, I only have to update the pages which are in cache. If the replication on the replica received a page change which is not in the page cache, I can just ignore it because I'm sitting on the same shared storage. I can always get it from the shared storage. Remember that the shared storage is a page version storage. So I can always ask the storage to give me the page at a certain moment in time, as we saw earlier. So here, one of our customers, GoGuardian, they were running bill log and were observing over 10 minutes of lag. But after they moved to Aurora, they added 4 replicas, and the maximum lag was consistently less than 20 milliseconds. So we talked about throughput, latencies. We talked about read scale out. What about write scale out? Aurora multi-master allows multiple writer in the same cluster in a given region. We made it generally available with 2-node multi-master earlier this year in Q3 2019. Aurora multi-master architecture, if we look at under the hood, is based upon 3 techniques. First, optimistic conflict resolution. And what I mean by that is, let's say I have 2 transactions, T1 and T2. And if both of them touching different pages, they can proceed in parallel. There is no coordination or synchronization required. However, if they both try to update the same page, then one of them will win and the other one will lose. And we're going to talk in detail how that exactly works. Second, because we push down the logging layer down in the storage, Aurora fundamentally decouples the physical conflicts between the pages in the storage node from the logical conflict between the transaction in the database nodes. And again, we're going to go with an example to talk in detail how exactly what I mean by that. Finally, we use a microservices architecture with independent, minimal, resilient services that are needed for asynchronous coordination. And any one of them temporarily going down does not impact the whole cluster. Let's dive deep into the optimistic conflict resolution and the decoupled system part. Here I have blue master on the left and orange master on the right with clients C1 and C2 respectively. Let's say both C1 and C2 started a transaction. And they both updated the same row of the same table at the same time. Anybody wants to guess what will happen? Any guesses? Yeah, exactly. So exactly. So what will happen is the storage node, what storage nodes will do, independently make a decision to accept from one of the database node and reject from the other. Because they're both updating, both the database nodes are updating the same data. And so in this case, C1 achieved majority of the votes, so it will commit and acknowledge back to the client, and C2 will roll back and ask the client to retry. Now, let's consider the same case again, but this time, C1 updates the row first. And at some point later, C2 gets the change. Now, from storage perspective, if I'm making the change in the latest version of the page, that's totally fine. Like from storage perspective, it's totally okay. But certainly not okay from database perspective. I cannot allow C2 to commit on uncommitted data from C1. And we detect that in the database node itself. And we do that using MVCC, which is a multi-version concurrency control. And essentially what that means is, if we see that we are trying to modify a row which has been uncommitted and from modified by a different node in the cluster, we immediately fail and roll back. And of course, C1 will commit and acknowledge back to the client. So hopefully you will also see that we don't have any centralized lock manager sitting somewhere that all these nodes have to talk and coordinate. This is all done asynchronously. And that's really important if you're trying to build a scalable architecture. So here, we were running 2 R4 4XLs. And we intentionally took down one of the R4 4XLs, but the other node continued to perform. And at some point later, we added R4 8XL, and so not only it scaled, but seamlessly took the traffic from the client application. The curve part that you guys see is buffer cache basically warming up. Okay, we talked about scaling, we talked about latencies, we talked about throughput. What about the complex queries? Like we push down log processing, we also push down query processing down to the storage, to thousands of nodes. Today, we can push down predicates, projections, functions, joins, and this is an active area of work for us. We get 3 key advantages out of this by pushing down the query processing. First, we are scaling down the query processing to thousands of machines. That's obvious, right? The second, we're pushing the compute where the data is. So imagine, let's say I have a line item table, one of size 1 terabyte. Rather than bringing the entire table into the memory and then running a filter, wouldn't it be much better to run the filter where the data is and across the thousands of storage nodes, right? And just get the filtered data back? Obviously, it will be significantly better. And let's say, the third, let's say magically, I can bring 1 terabyte quickly. Even if I can do that, it will still pollute the buffer pool. So all of your OLTP queries will start to suffer now because all of those caches or all of those pages will be evicted from the cache. So by pushing the query processing down, you're also not polluting the buffer pool and allowing your OLTP workload to continue to perform. In our TPCH-like workload, we observe 10 to 100 times better query performance with just this optimization. Okay, so much about performance and scaling. Let's talk about availability and durability. Aurora is significantly better when it comes to database restart. So the first thing to note is, let me preface this with this. What happens when database restart during planned and unplanned events? In a traditional world, we have to apply the redo logs since the last checkpoint in a single thread. And if you have a busy server, that can take time. With Aurora, we are already doing that work all the time. The pages are coalesced and distributed asynchronously in parallel all the time. So when database has to restart, we don't have to do anything special. All we have to do is figure out the last point at which we accepted the transaction. And that's it. And that's why it's significantly faster than replaying the entire redo logs from the last checkpoint in a single thread. Now you may argue, okay, this is good for database restarts. What happens if the hardware fails or if the entire availability zone fails? Well, with Aurora, you can have Aurora read replicas that we talked about before. And they also act as a failover target. In fact, you can define the failover order. And you can tell, hey, I want to, if this node, this master has to go down, I want this particular replica to be promoted. And that may be important for things like maybe you want your applications in certain availability zones, not in all the availability zones, just as an example. The other thing to note is, even though the replicas are 10 to 20 milliseconds behind, if the failover has to happen, there will be no loss of data. And the reason is because it's sitting on the same shared storage. So when we promote, we can ask the storage, what has changed between the master and replica, and what was the delta that I, as a replica, did not receive it. And I can ask that question to the storage, get the changes, apply it, and I'm good to go. Okay, so what happens, okay, machine failed, availability zone failed. Okay, I missed one thing. So we also announced, by the way, the support of ANSI read committed. This is for customers who are running long-running transactions. This will really help not halt the garbage collection process in MySQL. And if you have questions, I can take on this offline. So machine failed, availability zone failed. What about the whole region failed? We announced the support of Aurora global databases earlier this year. Aurora global databases provides two key benefits. One, the disaster recovery story. Second, low latency cross-region replicas. You can now have multiple cross-region replicas. They are supported in 5.7. You can upgrade your existing Aurora database in place to Aurora global database. And it is available in all the Aurora regions. So for DR, the RTO is less than a minute. That is, if the entire region goes down, you can fail over to a different region under a minute. And for low latency replicas, cross-region replicas, the lag is less than a second, even on the peak workload. And that is near synchronous. So how does it work internally? Well, we created a replicated distributed fleet that we connect as a slave on the primary region and connect as a writer on the slave regions. And then we do WAN optimized physical replication between the two replication fleets. And because it's physical replication, you get all the benefits of the Aurora read replicas that we were discussing before, as opposed to using logical replication. Now, there are other challenges, like how do you do DDLs, how do you handle patching, how do you handle failovers or failure scenarios. We hide all of that abstraction and complexity for you guys. All right, moving on to durability. First of all, why do we have 4 out of 6 quorum? Or why does AZ plus 1 failure matters? We believe that in the large distributed environment, machines can constantly go up and down. And as they're going up and down, there can be times when the entire availability zone can go down as well. And they can be correlated events. And we argue that for enterprise-grade reliability, we need to handle the correlated failures. And if we do simply 2 out of 3 quorum, and you can see that in the top left, if we have just done the 2 out of 3 quorum, and if we lost AZ3 and a copy in AZ1, then we lost both the copies. But if we do 4 out of 6 quorum, as you can see on the bottom left, even if we lost both the copies in AZ3, because AZ3 failed, and one of the copies in AZ1, we still must have 1 copy remaining because we wrote to 4 of the storage node at least. Now, in addition to AZ plus 1 tolerance, we also continuously stream the data back to S3. And we do that entirely in the storage node. And the way it works is we divide the entire Aurora storage volume into a set of segments. We periodically take snapshot of those segments and upload to S3, and then stream any changes that are happening after that to S3 as well. So when we have to restore, we take the latest, or at the time you specified as part of the point in time restore, we take the latest periodic snapshot and the delta changes after that and apply them in parallel asynchronously to construct the volume back. Now, there are times when, as an operator, we might have made a manual mistake. We forgot a where clause in the delete command, or we dropped the wrong table. So think of backtrack as a time dial, that you can bring your database back in time almost instantaneously. And this is much faster operation than trying to do restore, because depending upon the size of the volume, the restore may take some time. The other cool thing about this backtrack is, let's say you went to T2 and realized, oops, I made a mistake, I have to go back. And so you go back to time T1, but then you realize, oh my gosh, I went too far back. I need to go a little bit farther. You can do that. So none of these operations going back and forth is a destructive operation. So you can go back from T2, you can go back to T1, and you can go back to T1 dash, which is in between T1 and T2. And you will get your changes back. All right, let's move to manageability. Now, in any enterprise organization today, with the growth of data, ML is becoming, or machine learning is becoming, the integral part of the organization. Let's take a look at the product reviews as an example. You may want to find out the customers with a negative sentiment using Comprehend. Or you may have product orders. You may want to find out the fraudulent transactions using a fraud model running on a SageMaker. Today, if you have to do that, the workflow will look like this. You first will have to train the model. Then you have to write applications to read the data from the database, format it, send it to the machine learning service, get the output from that, format it again, and load it back in the application. I'm excited to introduce the integration of Aurora with machine learning services. First, I would also mention that before going into ML integration, I will also mention that we also announced SageMaker Autopilot that allows you to construct the models or create the models, best models, without you guys having to do a hit and trial on different algorithms. So it automates the model creation part itself. But coming back to integration of machine learning with Aurora, you can now invoke the models directly from the database using the SQL command. And we will automatically load the data, format it, call the machine learning services, do all the optimizations, and return the results back to you guys. And all of that is encapsulated. With Aurora today, we do a reasonably good job in managing the databases. Not only from the time-consuming administrative tasks, but also from things like scaling with storage, or scaling compute with serverless, or scaling read replicas with auto-scaling and custom endpoints, or integration with different AWS services. For example, Lambda for events, CloudWatch for audit logs and monitoring, IAM for better access control, S3 to load and export the data, and machine learning services for data science use cases. But still, customers with distributed applications have to self-manage their connection pools through third-party softwares to scale their applications. And not only that, for planned and unplanned database failovers, they affect the application availability. And finally, the credential management in the complex distributed application can be cumbersome and complex. I'm excited to introduce the preview of Amazon RDS Proxy. It allows customers to pool and share connections to scale applications with unpredictable workloads. You can have multiple proxies sitting in front of the same Aurora cluster. Second, it transparently tolerates transient failures without complex failure handling logic on the client side. And so what I mean by that is, if a master goes down, we will hold the connection on the proxy and redirect to the new master. So as a client, other than just some latency spike, you guys will not observe anything. And we will handle all the complexity of the failover inside the proxy itself. And moreover, because proxy is closer to database, we will completely bypass DNS, so it's much faster than having an external client relying upon DNS to switch over to happen. Because that's usually the bottleneck, especially with Aurora. Because our recovery is so fast, right? So the recovery happens so quick. But the DNS propagation itself takes several tens of or 20 to 30 seconds. And that's significantly more than what time Aurora takes to recover. And third, a unified credential management with AWS Secret Store. And what I mean by that, you can continue to use your database credentials, or you can use your IAM authentication. Both of them will work. And optionally, you can also enforce and tell that for RDS proxy, I just want to use IAM authentication. So you can enforce that as well. That is just for manageability. I should have pressed this earlier. So if you have any load issues and you want to monitor and root cause them, Performance Insight is the place. It can allow you to group by weights, SQL, hosts, users over time. And you can also group things by like SQL over hosts or weights over SQL. And then you can look at these metrics to identify the problem. And the problem could be I/O latency, high CPU. And once you identify the problem, you can then take actions like tuning your SQL query or adding more resources. The one thing I would say is the way we have integrated Performance Insight is done in a way that does not impact the database performance. Finally, with serverless, we can now manage your writer instance as well and automatically scale up and down all the way to 0 depending upon your workload. It is great if you have a sporadic for a dev test environment. Aurora Serverless is a great option. And the way briefly it works is by live migrating the connections from old machine to the new machine. If you want to learn more about that, I'll be happy to chat later after the talk. With that, I will hand over to DNA and Nintendo folks to talk about their success with Aurora and also to show you the cool video. Thank you.
Hello, everyone. I'm Kotaro Fukawa from Nintendo.
Hi, I'm Shunichi Kaneko from DNA in Japan.
I'm Yoshi Matsuzaki, database engineer of Aurora MySQL.
Hi, I'm Yutaka, solution architect for Aurora RDS MySQL team.
はい、今、動画でも紹介させていただいてましたが、スマートデバイス向けのタイトルでありますマリオカートツアーに関しましては、163の国と地域でサービスを開始しております。配信開始からおおよそ3ヶ月経ちましたが、ダウンロード数およびプレイいただいているユーザーの数に関しましては、任天堂の過去のタイトルの中で最高水準で推移しております。
So, Mario Kart Tour, our new gaming title for smartphones, which is introduced in the movie, was launched in 163 countries and regions. After 3 months passed since it was launched, the number of downloads and players are increasing fastest ever in our history. So, Mr. Fukawa, could you please let us know why you decided to use Amazon Aurora?
Okay. 我々はですね、このマリオカートツアーをサービス開始するにあたりまして、世界のすべての国のお客様に同時に遊んでいただきたいと思いまして、グローバルローンチ、いわゆる163の国に一斉に配信するということを決めました。このグローバルローンチに関しましては、システムにかかる負荷というのはすごい高いものがあるんですけれども、これを考えながら、特にデータベースに関しましては、ここに掲げさせてもらった3点がすごい重たい課題で、これを解決していく必要がありました。
So, firstly, we decided to launch Mario Kart Tour globally in 163 countries and regions to allow our customers all over the world to play at the same time. For the global launch, we had some difficulties that has to be solved prior to the launch. Especially for database, we had 3 core missions to be solved.
はい、1つ目に関しましては多くのユーザー様が一斉にアクセスされますので、ここに関して障害を発生させることなく安全に遊べるようにすること。2つ目に関しましてはユーザーのゲーム体験というのは非常に重要ですので、ここに影響ないようなハイパフォーマンスのデータベースであること。3つ目としましてはサーバーおよびオペレーションコストが最適化できることになります。今回我々はこのサービスを開始するにあたり、データベースとしてオーロラであれば解決できるのではないかと考えまして、オーロラを採用するというふうに行った次第です。
So the first mission is delivering a stability on our service without any availability issue, even if there are massive incoming accesses. The second mission is achieving high performance to prevent from poor customer experience. And third mission is optimizing server and operational cost. Considering the 3 missions, we decided to use Amazon Aurora because we thought it's an optimal way to accomplish the 3 missions.
So next we're going to show you that Mario Kart Tour's architecture. So Mr. Kaneko will describe that what was done on their side, and we're gonna also show you that how do they build their Amazon Aurora more reliable architectures. So as you can see, there's this slide. So they deploy that environment to the single regions. However, they use that full availability zone to keep that high availability stuff. So as a backend database server, they have decided to use Amazon Aurora MySQL. And this slide shows you that how big is that their environment. So on the release day, they have spin up that 600 instances, 600 clusters, and 1,200 Aura instances. So open the gates, so it means that starts the race. So traffic coming from that all over the world. So peak traffic achieves that 300,000 query per second, and storage size has reached 13 terabytes within a month. So next, we're going to show you that how to achieve that more high scalability environment. So stability is the most important thing to keep that stable gaming title. So Mr. Kaneko, what is the key point for achieving the high read-write performance? So first, I want to ask that for that write performance.
ライトのスケーラビリティっていうのは一番難しくて最も皆さんが興味があるところではないかというふうに思っています。私たちは水平分割を用いて想定の3倍のユーザーが来ても受け入れられるように十分なクラスタ数を用意するということにしました。
So for write workload, so scalability for workload performance is that difficult to solve. So they have decided to spin up the enough capacity to accept that traffic. So I want to ask you the next, how about the read performance scalability?
当然すべてのクラスタにはリーダーを用意して参照系のクエリはリーダーにすべて向けるというようなことをしています。オーロラであればリーダーのスケールをさせるということは非常に容易にできます。
So improve that read performance, they have spin up that reader instances for that read queries. So by using that Aurora readers, they can easily scale up their read performance. So next, we're going to show you that how to improve that performance tuning. So they have done the database tuning very well. So in addition to that basic MySQL tuning, they have also done the Aura MySQL specific tuning stuff. So most important thing to tune up that Aura performance in the Mario Kart Tour, they were using that closed beta test results. So what is the most effective tuning point in this environment?
はい、一番効果があったのはゴーストデータと呼ばれるものの保存方法を変更したことでした。マリオカートをプレイしているときに一緒に走るプレイヤーのデータがあると思います。あれがゴーストデータと呼ばれるものです。で、ゴーストデータは、プレイヤーが走ることを早くゴールをすると更新がかかるんですが、データサイズが非常に大きいので更新の負荷が非常に高いものになってました。そこで今回我々はオーロラではなくてゴーストデータを S3 に保存するというふうに変更しています。オーロラで持つデータとその他のデータストアで持つデータというものをしっかり判別して適切な場所に保存するということが大事だったと考えています。
So the most effective tuning point is that changing that store price of the ghost data. Ghost data stands for that virtual player. So when you play that Mario Kart Tour, so virtual player is also playing with you. So But for that, this ghost data is so update ratio is very low since this, the player achieves that best records. Only this time ghost data will be updated. But the ghost data size is big compared to that other customer data. So to reduce its disk I/O stuff, so they move to that ghost data to Amazon S3 from Aurora. So next question is that I has using the cross beta test result is good tips for the load test. So is there any other key point for the load test?
そうですね、一番のポイントは CBT の結果を生かしていかにリリース時と同様の状況を再現するかだったと思っています。我々は本番のリリース時と全く同等の環境を用意して世界中の AWS のリージョンから想定される負荷を流し続けました。また長時間にわたって負荷を流し続けるエイジングテストも合わせて行って、繰り返し改善を行い本番を迎えることができたと思っています。
So next key point is that using the load test environment which is the same production environment as much as possible. So to speed up that all components on that load test environment and doing the load test from multiple regions, it simulates that production workload to test the environment. So doing so, they can optimize their workload and tune up that all MySQL clusters. So next, we're going to show you how to eliminate these operational costs. So they basically used to use MySQL on EC2 for other gaming titles. So and also they have created and operated in-house mechanisms that can be achieved to the fast failover stuff and efficient load balancing environment. On the other hand, Aurora MySQL is full managed services. So they can be instance operation with single or few commands, and also failover and failure detection, the failure recovery is also fully managed by Aurora control plane. So by utilizing those functionality, they could reduce their operational costs. So please share, why did you build on fast failover system instead of the Aurora MySQL cluster has?
はい、オーロラのエンドポイントが DNS に反映されるまでにはやはりラグがありまして、どうしても長いと30秒から1分程度フェイルオーバーに時間がかかってしまいます。我々のオーロラでは10秒未満でフェイルオーバーするようにということをサービスレベルとして定めていますので、それを実現するためにフェイルオーバーの高速化というものに取り組みました。
So Aurora cluster endpoint and read endpoint change time is basically 13 seconds to less than 1 minute. So, but it is too long since that Nintendo and DNS is thinking that more fast failover is increase that customer player experiences. So that is the reason why they built a in-house fast failover mechanism instead of what MySQL has. So could you share more detail of your fast failover system?
私たちはですね、お客様に快適なゲーム環境、プレイ環境を提供するということを一番重要に思っています。したがって我々が提供しているゲームについてはデータベースのフェイルオーバーは10秒未満にするという形でサービスレベルを定めています。で我々がどうやってそれを実現しているかというと、オーロラの状態をリアルタイムにモニタリングをしてそれを独自の DNS に反映させるということをしています。アプリケーションはその DNS からオーロラのエンドポイントを引いて参照するということになりますので、それによって10秒未満のフェイルオーバーということが実現できているということになります。
So to increase that customer player experiences, So they define that failover time is less than 10 seconds. So to that's less than 10 seconds failover time, so they spin up that own DNS servers and the monitoring system. So this monitoring system to keep it watching that Aura cluster and the Aura instance status and detect the topology change in that cluster. Once detects the cluster topology change, this monitoring system modify their DNS servers. So all application server point to this in-house DNS servers. So to build this system, they can keep that less than 10 seconds fast failover system in that high load environment. So finally, we're going to show you that some graphs on Mario Kart tours. So this graph shows you that API requests per second on the release day. So you can see that after release that gaming title, Mario Kart Tour, this graph have been skyrocketed to the bottom to the up. So even if there's this traffic curve, also Aura MySQL cluster also accepts the same traffic curve queries. However, we can see that this graph shows you that latency on the Aura MySQL cluster side. You can see that Aura cluster provides a stable performance even if Aura MySQL cluster is under the high traffic conditions. So they can use, by using the Aura MySQL clusters, so Nintendo and the DNA can get the high performance environment, and they could greatly reduce that operational cost by using the Aura MySQL clusters, even if that's a very high load environment like Mario Kart tours. Yep. And that is under the hood of the Mario Kart tour. Thank you for joining our sessions. If you want to know about more detail of our database services, please visit the AWS.training website. Thank you for joining our sessions.
Thank you.